and this is the Gil Liebman Part 2 lecture on gases. Today we are going to start with the concept of gas density and molar mass. You can use the ideal gas law and the density of gas, and you can use them to find molar mass. So there's a relationship between Pivner density and molar mass. And here's a formula for you to memorize. Molar mass, measured in grams per mole, is equal to dirt over P, density times R times T over P. Density for a gas, however, as units of grams per liter. Pay attention to liter. You're used to density being grams per milliliter, but gases are very, 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 very light, and their density is measured in grams per liter. Okay, so molar mass is equal to dirt over P. Here's a sample problem asking you to calculate the molar mass of the gas. I'm going to use the dirt formula. What is Miss Gill going to do first? She's going to write down her givens. The problem gave you density is 1.50 atmosphere. Oops.
We'll try that. Density is 1.95.
Density is 1.95 grams per liter. Pressure is equal to 1.50 atmospheres. And temperature in Celsius is 27 degrees. We need to convert to Kelvin, 300 Kelvin. Okay, what's the formula?
Oh, Mrs. Lehman, I forgot.
What are we looking for? We're solving for molar mass. What are we looking for? Grams per mole. Okay, what's the formula? Molar mass is equal to dirt over P. So we will plug in our numbers. 1.95 grams per liter is density. R, do you remember R? 0.08206 liter atmospheres mole Kelvin. Write the units in. Memorize them. And T Kelvin 300. Divided by pressure, 1.50 atmospheres. Okay, let's check what units will cancel. Well, liters cancel, atmospheres cancel, Kelvin cancels, and what are you left with? Grams per mole, which are the units for molar mass. So multiply and divide, and your answer should be 32.0 grams per mole. Okay, notice that we use three significant figures. Okay, that should make sense to you. Now, if you were given a list of gases and asked what gas might this be, for instance, hydrogen, oxygen, or nitrogen, you would compare their molar masses to 32, and you would decide that this gas might possibly be oxygen. Of those three, it would certainly be oxygen. Okay, that's using the dirt formula. And tomorrow in class, ask us about STP. How this relates to STP. What we can do. Okay. Next law, Dalton's law of partial pressure, has to do with mixtures of gases. For a mixture of gas in a container, the total pressure exerted is the sum of the pressures of each gas. So if you had 3 or 4 gases in a container and you knew the pressures of each of those gases, the total pressure is the sum of them. Notice that R, T, and V will be the same for each gas because the gases are in the same tank, so their temperature and their volume is the same in this. The total pressure is equal to the individual pressures, P1, P2, P3. Those are called partial pressures, the pressure of each individual gas. And we can substitute in the ideal gas law and use that to find whatever it is we're looking for. Okay, Let's show you what I mean. P total is equal to P1, P2 plus P3. 3 gases or more in a mixture of gases.
But we want to substitute because we don't really ever use this really easy equation. Our problems are never this simple of just adding 3 numbers and getting P total. So we have to make this equation more useful to us. Find something else that P can be equal to, which is where the ideal gas law comes in. We take PV equals nRT, and now we're going to solve this for pressure because we can, whatever pressure is equal to, we could put up into our Dalton's law equation. Divide both sides by volume. And now we find out that our pressure is also equal to nRT over V. So wherever we have a P, a partial pressure up here, we can put in nRT over V. Well, since all of these gases are together, what are the common pieces of information? Our R, our T, and our V are all going to be the same because they're in the same tank. What's going to be unique about each of these parts is the moles. And you can designate these with numbers, make me N1, or if you wanted to, you could label the gas there. For example, if you had helium, you could put the symbol for helium beside of it. So now when we substitute this into our equation up here, P total is now equal to N1 RT over V, N2 RT over V, plus N3 RT over V, plus however many gases you have. Now, look at this. What can we do with this equation? What if we just wanted to solve for P total? Mrs. Liebman, what could we pull out of this equation?
Oh, looks to me like we could cancel the units that are common. No?
No,
Mrs. Liebman.
How could
I think Ms. Gill is going to answer
How
this
could we,
question.
how could we simplify this? Because R, T, and V are the same each place. So if we wanted to simplify it, P total could really be equal to N1 plus N2 plus N3 RT over V. So there's really a lot you can do with this Dalton's law of partial pressures law. There's lots of different ways to use it. If this totally confuses you, ignore Dalton's law and just think I've got to do lots of little ideal gas law problems, and then I'm going to add it up all at the end.
What I interpret Ms. Gill saying in that last formula is you take the total number of moles, right?
So we could even change this one to, give it a second, P total equals N total RT over V.
Okay. Crystal clear. Let's use it.
Let's try it.
Let's try it. Okay, here's an example. We have 2 gases, helium and oxygen, in a scuba diving tank. They tell us information about helium, 25 degrees Celsius, 1 atmosphere, 46 liters of helium, and oxygen, 12 liters, 25 degrees Celsius, 1 atmosphere. And those 2 gases are pumped into a tank with a volume of 5 liters. So look at what's happening. We're taking 46 liters of helium and 12 liters of oxygen and pumping them into a 5-liter tank. Notice that the temperature of both of the gases is 25 and the pressure of both gases is 1 atmosphere. And they ask us to calculate partial pressure of each gas and the total pressure in the tank. How are we going to start that problem, Mrs. Gill?
Well, I like to organize by gas.
So start with the givens. For helium, oxygen, and then the mixture in the tank. Okay.
Notice I automatically converted my temperature from Celsius to Kelvin. I didn't show my work.
Volume, temperature, and pressure for both gases. And what do we know about the tank? We know that it is 5 liters, same temperature.
What's going to happen, Mrs. Liebman?
Why, wow, we are taking 46 and 12, that's 58 liters of gas and pumping it, pushing it into a 5-liter tank. I do predict that the pressure will change. I do predict that the total pressure will be a whole lot larger, as will the pressure of oxygen and the pressure of helium. Okay. Is that what you predicted? What do we do first? Look at what you've got for helium. You've got V, you've got T, you've got P. What could we possibly solve for? Oh, I know. Pivnert. We can solve for N. Same for oxygen. So do it twice. Once for helium. We are going to isolate number of moles on the right-hand side. Divide both sides by RT. RT will cancel. You'll know that the number of moles is equal to PV over RT. And we are plugging in the numbers. P, V, R.
And Mrs. Liebman, I'm leaving out the unit this time.
Okay. But we truly believe that it will cancel and we will have moles. You can prove it at home if you want to. Now this is the number of moles of helium that we had originally, and that stays the same. That number of moles of helium is going to be the same in the tank. We're not changing the amount. Okay? And what you get when you do the problem should be 1.9 moles of helium. Do you know why Ms. Gill used 2 significant figures? I hope so. Okay. Now we're going to do the same thing for oxygen. Same formula. PV. V is 12.
Thank you.
R. And T is 298 Kelvin. Okay. No, oxygen is equal to, multiply and divide, decimal point 49 moles of oxygen. That's how much oxygen we had to begin with. That's how much hydrogen we had to begin with, helium we had to begin with, and that's the number of moles of each of those gases that is finally pumped into the tank, right? The only thing that changes is pressure.
Okay.
Okay.
And volume.
And volume changed, and now because of that, the pressure changes, right? So we need more space. Go to the next slide. And we are going to find the total pressure of the gas. It's equal to the partial pressure of helium over the partial pressure of oxygen. Remember what Ms. Gill just showed you, though. The pressures are equal to, and she showed you how she derived it, nRT over V. We know all of that. That's the partial pressure for helium and the partial pressure of oxygen. So the total pressure, when they are together.
Okay, Mrs. Liebman, I'm going to ask you a question. In here and here, what's the only number that's going to be different between these two?
The only number that is going to be different, Mrs. Gill, is N.
Is N. And what temperature are we using and what volume? Is it the temperature of helium or is it the temperature of the tank?
Well, since this is P tot, and that is the mixture of the gases together, I would say we are using the volume and the temperature of the tank. Do you agree with me,
I
guys?
agree.
All right.
Let's plug it in.
Let's plug it in. 298 is the temperature. The new volume we said was 5 liters.
I'll come back.
Number of moles of oxygen, RT. This is the equation that Ms. Gill derived for you on the couple of slides ago. Same volume. All right, so now we multiply and divide.
Now, don't rush to add these together because they asked you for the partial pressure of helium and the partial pressure of oxygen. And in this one problem, you get everything. Because remember, this is equal to the partial pressure of helium, and this is equal to the partial pressure of oxygen.
So solve each one separately. Sometimes P total is called P tot also, subscript TOT. Okay, she has very rapidly solved the problem, and there are our two partial pressures. So you have the answer, partial pressure for helium, partial pressure for oxygen. Add them together, and you have the total pressure, P total or P tot, as 11.7 atm.
And just a good reminder note here, this significant figure rule is different than this significant figure rule. When you do the multiplication and division step, that's one set of significant figure rule. And when you add the two numbers together, remember that's a different rule. So be careful of that.
Good point, Mrs. Gill. Okay, I suggest that you go back and try that problem on your own because there's a lot to learn right there. Okay, moving on a little bit to mole fractions. Mole fractions, or a mole fraction is the ratio of the number of moles of a given component in a mixture compared to the total number of moles in the mixture. It is represented by that X-looking symbol, which is the Greek letter chi, pronounced chi, and it represents the mole fraction. There are no units. It's just out of the total number of moles, how many moles are there?
Everybody stop for a second and cheer. There are no units on this
We don't
number.
have to cancel units. We just have to figure out what the fraction is. Okay? So, if you look at the mole fraction, it is equal to the number of moles of any gas over the total number of moles. And that gives you a decimal, and that's what you record as the answer. Okay? Don't leave it in fraction form. Leave it in decimal form, even though it's called mole fraction. Now, if you think about Pivnert, and you have a mixture of gases at the same temperature, the same pressure, the same temperature, the same volume, the same R, then the ratio of N to total N is going to be the same ratio as the individual pressure to the total pressure. So you can find the mole fraction of that gas by finding the partial pressure of that gas over the total pressure. Okay, this can be used to solve for mole fraction, partial pressure, or total pressure. And we are going to show you two problems. Problem number 1 gives you the partial pressure of oxygen in air and asks you to calculate the mole fraction. And then later, problem 2 gives you the mole fraction of nitrogen in air and asks you to calculate the partial pressure. Okay, so we get one of each. Let's try the first one first. How are we going to start number 1? We are going to start by writing down our givens. Pressure of oxygen is 156 torrs. Total pressure is the atmospheric pressure or the air pressure. Air is a mixture of many gases. 743 torrs. And you have to find the mole fraction. Chi for oxygen. Oh, that doesn't look so hard. Mole fraction for oxygen is equal to the number of moles of oxygen over the total number of moles.
What?
Or,
Mrs. Gill?
it's okay, just say or.
Or what
The pressure of oxygen, we just fake these, so that you'll be laughing at us a little. The pressure of oxygen over the total pressure works either way. Actually, it was a good mistake to make because that's important for you to know. Okay, so the mole fraction of oxygen is 156 over 743. Divide through, and you will know a number that has no units. But don't leave it in, even though it's called mole fraction, give us a decimal. We don't like fractions. Decimal 0.210. That's mole fraction for oxygen. Problem number 2. Now this time we're given the mole fraction of nitrogen as decimal 0.7808. Again, that's nitrogen and air. It's about right. A little over 3/4 of air moles is nitrogen, which our body inhales and exhales, cannot use. And the total atmospheric pressure here is 760 torrs, and they're asking you this time to calculate the partial pressure of nitrogen. So, Ms. Gill is writing the formula, which it says that the mole fraction of nitrogen is equal to the partial pressure of nitrogen over the total pressure.
I'm going to multiply both sides.
Multiplying both sides by total pressure to get total pressure, to get pressure of nitrogen alone.
And plug in.
Now, Ms. Gill, I have to ask you, do you require them to show the work where they're canceling units like that?
Yes, I am seriously mean, and I make them show all of their work. Because
She is seriously mean.
this is the equation everybody knows. This is a derived equation. So you have to show how you get from point A to point B.
Okay, everybody hear that?
I'm mean.
She's mean. Not. Okay, so there's total pressure, 760 times the mole fraction, a little over 3/4, and that's going to give us our partial pressure of nitrogen. Multiply through, you'll get pressure, this time units, torrs. Does that look right? Is that about 3/4? Yes, it is. That looks fine to me. Now, wait a second. There's something I don't like there. Torrs. Oh, never mind. I like it just fine. I just mixed up what number was which. Okay, no problem. So, try those on your own and see if they make sense to you. Okay, it'll just take a couple minutes. Now, vapor pressure, when you collect a gas, many gases look just like air. So how do you know when the bottle is full of the gas? You don't. So you often will fill the container or the bottle or the glass with water and then bubble the gas through the water, and the water will be pushed out of the container, and you'll be able to tell when it's full of gas because there'll be no more water left. The problem with that is that a little bit of the water will evaporate into the gas. So when a gas is collected by water displacement, you end up with a mixture of gases. One of them is the desired gas, and the other one is the water vapor. I'll give you a hint. Actually, I'll wait because it's the last thing that's stated on the slide. So we'll talk about that in a minute. Okay, now you're going to know to be concerned about this if it says the problem was collected by water displacement, or if it says the gas was collected over water. Same thing. They're telling you that there's a little bit of water vapor in there and it's not just the pure gas. Okay. How does that happen? Well, water vapor escapes from the surface of the water. Some escapes from the surface of the water, and it collects above the liquid. And at the same time, some water vapor returns back or condenses back into the liquid state. A picture. There's the liquid water. It's a closed container. some, we'll come back, some liquid water becomes vapor, and at the same or gas, and at the same time, some of the gas condenses back into the liquid. When it's a closed container, and when the amount of gas escaping, or the number of molecules escaping, equal the number of molecules returning, the vapor pressure will be constant, because it's the vapor that causes the pressure. And that state is called equilibrium. We love equilibrium, so pay attention whenever we mention the word equilibrium. Notice that the vapor pressure of water depends on temperature. As temperature increases, more liquid vaporizes, which is logical, and we have more vapor. You will be given it, or you'll look it up. It's easy to find. Information is easy to find. Let's do a sample problem there, Miss Gill. Okay, so let's look at this problem. We have solid, note, solid potassium chlorate. It's heated in a test tube. It decomposes into potassium chloride, which is a solid, and oxygen, which you know is a gas. Oxygen is collected by water displacement. They're giving us some information about it. They're giving us temperature, pressure, volume, and the vapor pressure of water. Second clue. Not only did they say it was collected by displacement of water, they also gave us the water vapor pressure at that temperature. Now we're asked to find two things: partial pressure of oxygen and the mass of potassium chlorate.
Remember, that's a solid.
That's a solid. All right, so we have solid potassium chlorate. It is undergoing a chemical reaction called decomposition, forming potassium chloride and oxygen. What's the first thing we have to do? We have to write a balanced equation. You know, when I was in high school, we actually did this lab, but it uses an open flame and oxygen gas, and over the centuries, they've decided that that was not a safe experiment to do anymore. Okay, so now what are we given? 22 degrees Celsius, a total pressure of 754 torrs, and a volume of decimal point 650. And we know something else, don't we? We know the vapor pressure, or the pressure of the water vapor, and it is 21 torrs. Okay, so if the total pressure is 754 and the water vapor pressure is 21 torrs, that should be a pretty easy equation. Can they just do it, Ms. Gill, or do they have to show you a formula?
They at least have to show me some work. But whose law are we using here, Mrs. Liebman?
Oh, it's not Gill-Liebman law. It is Dalton's law of partial pressure, because the total pressure is equal to the pressure of oxygen and the pressure of water vapor. All right, so
We finally do get to do an easy one, except we're not adding this time. We are going to...
what are we going to do if we're not adding? We're looking for the pressure of oxygen. Oh, I think you know, guys. We are going to subtract, and the partial pressure of oxygen is going to equal 733 torrs. All right, here we go. That looks pretty good. So now I know the pressure of oxygen. I know the volume of oxygen. I know the temperature of oxygen, but. If it's a gas, it has to be in Kelvin. So I know P, I know V, and I know T.
I know. We're using the ideal gas law.
Yes, you are. So here we go. Ideal gas law. All right. And we are solving for who? We are solving for N, right, everybody? So she is going to isolate N by dividing both sides by RT. PV over RT equals N for oxygen. All right, plug the numbers in, 754 torrs. No, she doesn't want to do it yet. What?
What's the problem, Mrs. Liebman?
Oh my goodness, good point. Not only did we have to change temperature units, This was way too easy before. We have to change pressure units to atmospheres. Do you remember? We have 733 torrs. 1 atmosphere is equal to 760 torrs. We're doing that because of the units in R. We have not memorized the units of R in torrs. So we're just converting to atmospheres. Now she can do it. So pressure is decimal point 964. Volume is decimal point 650. R and T 298. Units will cancel. We will be left with moles to multiply and divide. And you will get the number of moles as decimal point 0259 moles of oxygen, 3 sig figs, and all the problems. Beautiful. That's wonderful. However, that is not what they asked us for.
Not what they asked us for. But why did we have to solve for this part, Mrs. Liebman?
Why did we have to solve for moles of oxygen?
Can I use the ideal gas law with a solid?
No, never. You can only use the ideal gas law with gases. And while that sounds obvious to you now, sometimes people forget.
But now that I know how many moles of oxygen I have, what can I use to get to grams?
We must do some stoichiometry.
And I'm out of space on this slide, so do it at home and check your answer.
Okay, so what you're going to do is you're going to do a mole conversion from moles of oxygen to moles of potassium chlorate. You're going to find the molar mass of potassium chlorate and then the grams of potassium chlorate. The answer you should get is 2.12 grams. Spend a couple of minutes and do it. It's worth your time. Come in tomorrow and ask questions if you have them. And I know this is going to disappoint you, but this is the end of Gil Liebman for today. See you tomorrow. Bye.